Okay, so good afternoon. Our speaker today is Alessandro Peca, who's a fifth-year graduate student at the University of Miami, the US, under the supervision of Nico Cappelluti. Previously, he was a master's student here, working with Christian Vignali. He's an expert on X-ray surveys in the obscure AGN universe, and today he's going to tell us something more about that. Please.
Thank you. So thank you for having me here today. So today I'm going to show you what I did during my PhD, what I'm still doing, which is about using large area surveys and more in general, big data to discover obscure AGN in the universe. Okay. This is not working.
1 second.
Okay. Okay. Good. So the mic.
If you're okay. No, we see this.
Nice.
Mirror display.
Qua sopra.
No, guardare questo. Ah, non
No, è che ho perso il mouse.
Ok.
Ok, adesso ce l'ho.
Qui.
Qui. Screen. No.
Secondo me il mirror profile swap displays. Swap.
Vedete quello? Ok, ma non si vede.
Sullo schermo.
Vabbè, ma loro lo vedono
Sì.
grande.
Ok.
Quindi facciamo quello bene. Ok. Okay, so this is my outline. So I'm going to introduce you why we are studying obscure AGN and why we think there is a problem with obscuration. And to answer and to solve this problem, I'm going to propose you two different solutions. The first one is using large area X-ray surveys. And the second one is about the AGN-DataBase, which is a beautiful database that we are building in Miami. So why do we think we have a problem with obscured AGN? Well, when we speak about obscured AGN, we need to start from the X-ray background. So here you can see one of the many studies on the X-ray background. You can see the orange points, while the black and gray line is the best fit model. And we believe that the origin of the cosmic X-ray background is a population of unresolved AGNs across the entire universe. And except for this green line here, which is the contribution from the host galaxies, all the other color lines are different contribution of different AGN populations divided by absorbing column density. So what we can do is to play with AGN population synthesis models and try to reproduce the entire X-ray background by including different AGN populations. And in particular, I want you to focus on this red curve here, which shows you the contribution of Compton-thick AGNs. A Compton-thick AGN is defined as an AGN with line-of-sight column densities in log scale more than 24. And since we have AGN population synthesis models, we can predict the spatial density of all these AGN, and we can infer the number of them. But the point is, do we see them in observations? And the answer is that no, not very well. This is just an example by Torres Alba 21 and later updated by Drugo. So the authors here took the 100-month SwiftBat catalog, which is a very nice catalog if you're looking for obscuration, because SwiftBat is able to collect photons up to more than 100 keV, which is super good if you're looking for obscuration. And if you check the cumulative distribution of observed Compton-thick fraction, meaning number of Compton-thick AGN divided by total number of AGNs, in the local redshift, so at redshift up to 0.5, we have around 8% of Compton-thick AGNs. But when you take into account population synthesis models, you have a predicted fraction of Compton-thick AGNs which is between 20 and 50%. However, even if we are almost unbiased in Swift beta against obscuration, we are still limited by the limiting fluxes of the catalog. But if you take this model, for example, the ANANA 19 model, and you apply the observational biases and selection biases to this sample, you get an expected fraction of Compton-thick sources, which is about 27-38%. So there is a huge gap. And even if you take the WEDA 14 model, which predicts a little bit less obscuration, you still don't get 8%. So there is a discrepancy here between what model predicts and what we see in observations. Moreover, we know that from several studies that obscuration increases with redshift, and also heavily obscured AGN like Compton-thick AGNs are extremely faint in the local universe, so they are probably more fainter in the high redshift universe. And this is to say that we know that there is a discrepancy locally, so we expect that this discrepancy is higher at high redshift. So the question is, how can we solve it? And is this the only question that we have about obscuration? So this is not the only question, because studying obscured AGN is important for many, many reasons. For example, we don't know the nature of the obscurant. So we know that from X-rays, we can get the line of sight obscuration. However, we know that there is a contribution from the inner torus and the host galaxy. But there are several works on the topic, but we still don't know very well the contribution of both these components. And this is, of course, important when you study the coevolution between supermassive black hole and the host galaxy. Also, we are now living in the JWST era, and every day in the archive, there are new discovered galaxies at very high redshift, and some of them are lacking AGN signatures. And some authors are claiming that we don't get the AGN signatures because the AGN is buried under a very thick column density, but is really like that. How can we say that? We still have a lot of work to do. And finally, of course, tracing obscuration is also important for the primordial black hole models. As you may know, we have two different models, the light and heavy seeds of primordial black holes, and we expect them to be obscured. So this is why obscuration in AGNs is very important. So how can we solve all these questions? We go to solution A. So solution A is using large area X-ray surveys. Why? So here you can see on the right the so-called wedding cake diagram, which is basically telling you the same thing you can see here, area versus limiting flux of some of the most famous surveys in the literature. And this slide is telling you that we don't have the perfect telescope, so we cannot get faint sources in large areas at the same time. So if you take an X-ray luminosity function, whatever luminosity function, you can see that there is a drop at high luminosities. So this is telling you that in this high luminosity regime, these objects are rare. So to sample them, we need to sample large volume of the universe. And high luminosity AGNs are also important because we know from theoretical models about supermassive black hole evolution that high luminosity and high NH AGNs are in a very important key phase of the evolution, in which the bulk of the mass is accreting into the central black hole. So this is why it's important to get at the same time high luminosity and high NH AGNs. So we use the Strive 82X survey, which is a large area surveys covered by XMM and Chandra over more than 31 square degrees. We have a high redshift completeness. We have a multi-band coverage over 25 bands, which can give us very important complementary information. But also we have numbers because we have more than 6,000 unique sources, but also 1,500 hard band detected sources, which is always good when you are looking for obscuration. And this is a sketch of what we did. We started from the La Massa 16 master catalog, then we made some redshift and X-ray spectral quality cuts, meaning that we took only sources with spectroscopic or good quality photometric redshifts. And also we made an extensive use of MCMC simulations to get the minimum number of X-ray photons for which you can get a reliable fit. So at the end of these cuts, we got a final sample of around 3,000 AGN candidates. So this is one of our results. Here you can see as a function of redshift, the intrinsic X-ray luminosities. The yellow points are our points, and you can see how well we sample the high luminosity part of this plot, and we share the area with other X-ray sources. However, for some reason, I'm obsessed with obscuration. So when I was looking at this plot, I was also looking at these purple points from the Chandra deep field south. And here there are many obscured and low luminosity objects. So my question was, how many AGNs are we missing with striped T2X? To answer this question, I did some simulations. So here you can see, so this is a representation of what we did. So this is a perfect telescope, meaning that as a function of, for example, an age and redshift, on the z-axis, you have the percentage of sources that you can get in your observations. So of course, if your telescope is perfect, you get 100% for all possible combination of parameters. And then we simulated a lot of sources as a function of redshift, LX, and an age. What we did next was to apply our observational limits and observational biases to our simulations. So when you do that, what you get is something like this. This is a three-dimensional histogram. Then as a function of physical parameters, gives you the percentage of sources that you get in striped T2X. Meaning that 1 minus D is the percentage of sources that you are losing in striped T2X. So these are percentages. So you can apply them as corrections to our observed distributions without assuming any luminosity function. And here is just an example to show you our distribution of absorption, LX, and gamma. And the result of that is we had intrinsic numbers. And when I say intrinsic numbers, it means that we were able to analyze what we see in the data, but also what we don't see because we missed that. And once we had intrinsic numbers, this is one of the things we did. Here you can see the fraction of obscured AGN as a function of redshift for 3 different luminosities. Unfortunately, we found only 2 Compton-thick AGNs. So we didn't include in our pipeline Compton-thick AGNs. So everything you see here is up to log NH 24. And you can clearly see how at all the luminosities, at least between log LX 43 and 46, as a function of redshift, there is a clear evolution. So obscuration in AGN increases with redshift. And we are particularly proud about this plot here on the right that is basically telling you that we were able to put very solid constraints in this high luminosity regime. So you can flip this plot. So this is the same absorbed fraction of AGNs, this time as a function of luminosity for different redshift beams. Again, here you can see that there is an anticorrelation with the luminosities. And just to let you know that we fitted all these points. And if you want to play with this models, just go on our paper and please use our models. But also we did more. Now, I don't have too much time to go into the details, but because we had intrinsic numbers, we built our own X-ray luminosity function. But also we were able to disentangle the obscured and unobscured part of the luminosity function. So again, if you want to play with numbers and you want to see how many AGNs, obscured and unobscured, you can have in your surveys, you can take our models. We were also able to make some prediction of Compton-thick AGNs using black hole accretion density evolution, and everything is mentioned in our paper. However, coming back to the initial question, how can we improve these results? Oops. How can we improve these results? So we won this nice Chandra archival proposal because everything I showed you is from the beginning of Chandra XMM up to 2016. So from 2016 to nowadays, you have available in the archives all this red Chandra, green XMM new observations. So we decided to include them and to produce a new updated catalog, which in some overlapping regions is 2 times deeper. We have more than 5 times the numbers of AGNs, and we now reach a total area of around 55 square degrees. So our expectations is to expand our study to redshift larger than 4, even higher luminosities, but also we really hope to find some Compton-thick sources to include in our analysis. So this is what we have right now. We have a total number of more than 23K sources. And if you just plot the fluxes, you can see compared to the old survey, how many new sources we have. And also here at lower fluxes, I really hope to find very obscure AGN. I already matched the new catalog with multiband counterparts. We have a 92% of X-ray sources with at least 1 multiband counterpart. We did the matching with Lyra, which is a maximum likelihood estimator that I wrote, and it includes Bayesian statistics and is also able to automatically find priors of magnitude, densities, completeness priors, and you can add even more of them. But let's go to solution B, the AGN-DataBase. So I showed you how large area X-ray surveys can help us in understanding obscuration in AGNs up to very high redshift. So the next step can be the Strike82XL, as I showed you, or one can say, why don't you add other surveys to your study? But we were like, why don't we add all the AGNs that we have in the literature? Literally all of them. So we started building our AGN-DataBase. So AGN-DB is the repository of all the discovered AGNs at all the wavelengths and all the redshifts. And it has information on redshift, of course, but we have also classification, photometry, images, SEDs, and in next month, we will also include spectroscopy. So how we built such a database? Well, first of all, we went into the literature. We downloaded all the catalogs of AGNs, and we stored them together. Then we built our pipeline. So our pipeline is able to unify all the units to the standard CGS system, is able to deal with all the kinds of catalog formats, and we merge overlapping catalogs together with Lyra. And the nicest thing is that we can ingest new catalogs almost automatically. This means that if you tomorrow publish a new catalog of AGN, in a couple of days, we can include it in our pipeline. The output of our pipeline is a single, unique, huge master catalog. And we are also developing a website in which people can make queries, of course, download the results, and have access to images, SEDs, and also spectra. So this is a preview of what we have. So this is a projection of the universe. This is a density plot. And this is showing you that right now we have around 7.5 million unique AGNs. And these shapes here are like the SDSS stripes, meaning that it's just telling you that in some areas of the universe, we have more observations. And so we also discovered more AGNs. So these are just some of the numbers that we have: high redshift completeness, 66 magnitude and flux bands, almost 1 million of X-ray sources, several millions of near-infrared, mid-infrared, far-infrared, optical, and also something about gamma band. But why the AGN-DataBase can help us in understanding obscuration AGN? Well, because we decided to solve all these issues with obscuration by using big numbers. This is not the only solution. This is our solution. And AGN-DB is probably the best tool to do that because we have all of them. So right now, I'm doing the X-ray spectral analysis on the entire catalog. Right now, we have only classified AGNs, meaning that there are a lot of catalogs without classification or without solid classification. So the next step is to match all these catalogs without classification with our AGNs to increase the completeness. Also, we have a student working on SCD fitting over the entire database to get AGN and host galaxy properties. And this is something I really would like to do, is to build a multi-band and volumetric luminosity function. Why? Well, again, just because we can, because this is probably the best repository of AGN, so the best place to build such a multi-band luminosity function. Also, a student that unfortunately now left, he started looking with some machine learning tools to a misclassification project. So right now, if somebody classified an object as an AGN, we have it as an AGN in our database. However, we found out that some classification, even spectroscopic classification, may not be so accurate. So we have this possible open project, so to start making our own classification, or at least start to see if there are many misclassified objects. And also we are collaborating with Yale to get the morphological classification of the host galaxies of these AGNs. And also we are computing as many as black hole masses as we can. This is my summary. So I showed you how we have a discrepancy between observations and models. We want to solve the discrepancies. In particular, in STRIPE82X, we found out that, I didn't have the time to show it to you, but the ANANA 19 model, which is the one that predicts more obscuration than the other models, is the one that fits well with our data. So the one that works better, meaning that this discrepancy can be even higher, as previously thought. We are trying to solve all these issues by using two different solutions, wide area X-ray surveys, but also we don't want to limit our study to X-ray, so we want to include all the possible information, and this is why we built the AGN database. And let me conclude by saying that big data repositories like AGN-DB and other multi-band surveys are not only about obscuration, but they really open many new opportunities, which are about multi-band luminosity functions, host galaxy properties, black hole masses, mixed classifications, and really everything you can have in mind. If I have one more minute, I'm going to show you our database. So it looks like a very simple web page. Then you go on search, and you can make queries. Like in this case, I selected a redshift larger than 5, and you get a table with array and DEC and all the magnitudes and everything we have. However, when you click on one, so each line here is a unique AGN. So when you click on one of them, you get something like this. So on the left, you have, of course, array and DEC, redshift, photometry, morphology, and classification. Then we are interfaced with IPS2FITS, which is a NASA database that gives you images. And also we have our Sigali version, meaning that you can see our fit, but you can also use Sigali directly on our webpage. So you can just set the parameters and click on generate ACD, and it works, and you can download everything. And thank you for your attention. I'm happy to take any questions.
Should move here for questions. So, any questions for the speaker? Yes, please.
So in the first solution that you proposed, using large database, can you explain more how do you to construct the fraction of objects that you miss as a function of redshift and age? How do you need to assume that you know the perfect telescope, right? Construct
The what? Sorry.
Like the perfect telescope, the real universe.
Well, that was an example. So when you simulate a lot of fake spectra, you are basically producing, like, it's like you have a perfect telescope, right? You can produce spectra that in reality you don't see. So what you can do is to apply response matrices, like in the axis, like RF, RMF, ARF, whatever. You can take into account exposure time, so you can make a cut on what you simulate. So you can get how many sources, the percentage of sources that you are getting and you are losing. So if you have that and you have observed data, is a percentage, so you can reconstruct the intrinsic numbers. The only caveat of this is that, for example, because we didn't find any, actually we found 2 Compton-thick sources, but 2 is such a slow number, so it's like we didn't find Compton-thick sources. We cannot correct for what we don't see. So if I tell you that we are missing 100% of the Compton-thick sources, but we see 0 sources, 100% times 0 is 0. So that's it.
Then there was Christian.
Is there any level of homogenization in your catalogs? For example, in the 72, did you consider also the different versions of the database?
One second. One question was, is there a level of homogenization in the catalogs? We don't have the mic.
Yes. So I'm going to tell you what I think the student that is working on that is doing. So I would say yes, meaning that right now the student, she's just at the beginning, so probably she's not considering all of that. But we can do it since we store all the technical information in our database. So for each AGN, you can always go back and check from what catalogs we got all the information. And so, so I would say we can. I'm not sure we are doing it.
That's because you're taking the values from the catalogs and you're now able to sort it.
Correct.
Do you plan on doing photography?
I don't. Maybe new students, I don't know. You should ask my advisor. I don't think so.
And are you also ready to merge in the catalog all the new AGN that are going to be probably delivered by radio surveys in both hemispheres?
Everything that is published,
okay,
we can include it.
So be ready to include the ERAS-1 AGN sample that will be released on January 31st.
Okay, so now when?
January 31st, last day of January.
Okay, okay. Yeah, but I'm waiting for that, even for other things. Yeah.
If is already included.
Yes.
okay. Any more? Yeah.
In the database, do you include or do you plan to include also information on the optical accretion?
Optical?
Accretion.
Yes. So what we are doing right now, so when we present the database in talks like this one, we also ask for feedbacks. So right now we have what we think is useful, but sometimes it happens that people are asking me, for example, optical obscuration, so we can add it. So the first version of the catalog that will be published before the end, I mean, I'm going to submit the paper before the end of the next spring. We will not have it. We will have obscuration DXs, but this is going to be like version 1.0, so we can expand it, including like people is asking us about variability, something that we are planning to include. Yeah.
Let me check if there are questions online. No, that was already before. Okay, any more questions from here? No. So, okay, we can thank